Okay, so we're very happy to have Gabriel with us today, and he's going to talk about range polynomial protocols.
Hey, so yeah, thanks very much for inviting me. Though I did invite myself a little, and then I was invited. I'm uh, I'm really excited to sort of the motivation for this talk is I've been more in the practical zero knowledge space in the last few years. So I don't know if people are aware, but zero knowledge proofs are pretty big in industry now. There's lots of companies and startups working on them. And sort of this talk, kind of what I wanted is for smart people to think about the questions that are relevant to us. So I tried to phrase one of these questions in sort of this mathematical way that has nothing to do with cryptography. So I'm curious how this will be received, if it will seem natural or interesting or not. And I apologize in advance. There's probably going to be some, since this is sort of the first time I've given this sort of talk to people who are not with all the sort of certain zero knowledge context, I'm probably going to mess up at some point. Like there's probably going to be things that are not as well defined as I thought. So apologies in advance. And at the same time, please feel free to completely derail the lecture with your questions if it's just like it gets to a point where I try to give a little context of sort of, but it's probably not enough. So feel free to derail the talk with questions like, you know, what does this have to do with anything? I'd be happy to go on a tangent and give more sort of context. So really feel free. Okay. So yeah, Aztec is the company I work for. I didn't know it was related to something from combinatorics. I think originally it stood for anonymous zero knowledge transactions on Ethereum, and I forgot what the C was. Well, okay, so like I said, I want to start with a few slides of motivation and context. So sort of this notion of polynomial protocols that I'm going to present, it comes from kind of trying to get zero knowledge proofs in practice as efficient as possible. Really, like it's a lot of work on the constants in prover running times. Okay, so these first few slides will be pretty informal. So what we're talking about here is this thing called succinct arguments. And informally, sort of what are they? So we have some program or circuit that is known to everybody, and we have some public output of this program. And generally, the kind of things we're interested in is we want to make proofs of statements of the form, I know some input X to this program that will lead to output Z. So, right, sort of the natural way to make such a proof is to give someone X and have them execute the program. But right, two things: the size of X, you know, might be as sort of as large as the running time of T. Verifying the proof this way will require executing T. And of course, we might just want to prove knowledge of X and without leaking X. And of course, doing it this way will leak all the information about X. So we want to have proofs of statements like this, where the proof size and verification time are much smaller than the runtime of T. So this has this is sort of the motivation for this acronym that you will see a lot in the practical zero knowledge space, or also I guess the theoretical, SNARK, which stands for Succinct Non-Interactive Argument of Knowledge. Right, we want a short proof that is quickly verifiable, and hopefully the proof is just, it's not an interactive protocol, it's just one message that proves we know such X. Cool. Now, I'm really compressing here decades of work in one sentence, but basically the approach for how to do succinct proofs is something called arithmetization, which started, I think, arguably started with this classic work of Land, Fortnow, Karlov, Nissan that gave us Co-NP is an IP. And basically the approach is to reduce the claim I'm interested in, like I know the input X for program T that makes output Z, to reduce it to some claim from the world of polynomials. So reduce it to some claim, I know a bunch of polynomials that satisfy some polynomial identity. So, and again, very broadly, when we're interested in small proofs, why do we like polynomials? Because when I have a claim about polynomials, right, from the famous Schwarzschild lemma, it's enough to check the claim on a random point. So, right, so if you claim to me, I have a bunch of polynomials that satisfy some identity, then checking if you just give me the values of the polynomials on some randomly chosen point that you had no control over, and I just check the identity at this point, I will be convinced with very high probability. But of course, to make this thing work, we have like this chicken and egg problem. Like I want this short proof, so I want you just to give me the evaluations of your polynomials on some random challenge point. I don't want you to give me the whole polynomials. But of course, there's a big chicken and egg problem to do something like this. Because if you give me the evaluations after I told you the challenge point, then you're going to adaptively choose polynomials that work well on this specific challenge point. So the prover, we need mechanisms for the prover to be committed to his choice of polynomials before he sees the challenge point. And so this thing relates to a lot of work in theoretical computer science and the PCP literature. It relates to this whole work on what's called low degree testing and PCPs of proximity that I won't get into. But sort of also what's happened in the last decade is that people have used sort of cryptography to address this problem. And if you think of it, the sort of primitive that's relevant here is what we can call a polynomial commitment scheme. So this notion was first defined in this work of Kate Zawarucha Goldberg, which has become extremely important in the in particular in the sort of practical zero knowledge space. So what's the idea of a polynomial commitment scheme? The idea is that the prover here, it's a scheme where a prover can send a short commitment to a polynomial. And then later, a verifier can choose some element in the field. And then the prover can send just the value of the z of the polynomial on this point, together with a proof, let's call the proof open fi, that this is really the value of the f that the prover had in mind during commitment time. So a bit imprecisely, speaking practically, this KZG polynomial commitment scheme, it gives us both commitments and opening proofs that are only, in practice, they're only 32 bytes long. Basically, whatever there is some theoretical bound, but basically for any degree that will ever come up in practice, a million, a billion, the openings and commitments are 32 bytes. So I want to give you a short exposition for what this polynomial commitment scheme looks like. If you've never...
Quick question, Ariel.
Yeah.
Okay, maybe I'll ask, maybe it's more appropriate later, but in terms of post-quantum alternatives, has anything happened on this front? Like, is there any reasonable post-quantum alternative here?
Well, I think the only known post-quantum alternative is, if you look at the work on low-degree testing, and the latest for univariate polynomials is this work of Eli, Ben-Sasson, and others. They call it FRI, Fast Read Solomon Interactive something. I forgot the exact acronym. But basically, you can look at low-degree techniques that have been developed, low-degree testing techniques. You can look at them as a polynomial commitment scheme. There are works that have done this explicitly. And that gives you a quantum-resistant polynomial commitment scheme. But the efficiency is orders of magnitude worse.
Mm-hmm. Okay. But under lattices, for instance, nothing better is known than the FRI-based IOPs.
Oh, that I am not 100% sure. If someone hasn't constructed something from lattices. I haven't seen it, but I'm not totally sure.
Mm-hmm.
It's a good question. Okay, so I want to give you I want to show you how this polynomial commitment scheme looks like. If you've never seen elliptic curve pairings, it may be hard to follow, but again, this is sort of just part of the motivation part of the talk, so it's not terrible if you won't follow the next slide. So let's just use this notation, like x in brackets. Let's think of it as an encoding of x, and just what I mean by it, it's g to the x, where g is a generator of some elliptic curve group, which just the important property is that the discrete log problem is hard. So it's hard to get x back from seeing this encoding of x. Right, so how does this polynomial commitment scheme look like? So first of all, you need what's called a trusted setup for this scheme. So we need someone to choose an x that, we need somehow to choose an x that nobody knows, and then generate this string of the powers of x, like, right, these are encoding, so like the powers of x in the exponent. And we need somehow to generate a string that looks like this for x that nobody knows. So how to do this is a whole other thing that is very important in the sort of practical zero knowledge world. We need to do these multi-party computation protocols where we generate something that looks like this for random x that nobody knows. And this requires some multi-party computation, but let's say we have a string like this. We have this for a secret x that nobody knows. And now the commitment of x to f will just be the just g to the f of x, right? And since we can, if we know f, we can compute from the setup. We can compute this commitment just by linear combination. And now, say I want to open f at I, then the opening proof will be the encoding of another polynomial h of x, where h of x is this polynomial f of x minus f of I divided by x minus I. So right, so if I look at f of x minus f of I, it's going to be 0 at I, obviously. So it's going to be divisible by x minus I. So this thing is really a polynomial. It's not a rational function. And so the opening proof will be just the encoding of this polynomial. And now how does verification work? So the verifier, he has the commitment to f, he has the opening proof, he has the alleged value of fi, which is z, and he has I. So the verification is going to use what's called a pairing. And basically what pairings let you do, if you've never seen them, is they allow you to, if you have things in the exponent, like x and y, g to the x and g to the y, it allows you to basically multiply things in the exponent. It basically allows you to check some product in the exponent. So with the pairing, we're just going to check that that really we have that the commitment minus the alleged value is equal to h times x minus I. Right.
So Ariel, just to make clear, the verifier doesn't need to know x, right? All this is done with x being hidden, also from the verifier.
Also from the verifier. Mm-hmm.
So
yeah, right. So. Mm-hmm.
Is there any kind of proof of security for these things?
Yes. So the proofs so just right. So the verifier can compute this encoding of x minus I just from knowing I, right? Because of having the encoding of x in the setup. Yeah, the proof for this requires very strong versions of. You can think of it as very strong versions of the discrete log. But it's what's called non-falsifiable assumptions. So basically what people use to prove this lately is something that's called the algebraic group model.
Just a comment that when you shop at Amazon, the protocol is analyzing something known as the random oracle model. which also assumes that you have, it kind of models the practical hash function as a random function, which doesn't exist in practice. So people make this heuristic leap of faith all the time. So here you have a clean information theoretic proof. If you model a bilinear group as a random bilinear group, so take a big group ZP times ZP, pick a random bilinear function, and then the protocol is provably secure in this model. And then you can either take a heuristic leap of faith and assume that elliptic curve instantiations are still okay, analogously to the random oracle model heuristic that you use when you shop at Amazon. Or you can take an alternative route and try to formulate concrete assumptions or the algebraic group model that Ariel mentioned. So these are two parallel routes. I think that in practice, we don't have yet a natural example of something which is provably secure in the generic model and fails in terms of practical attacks. Correct me if I'm wrong, or maybe if there are such examples, they're controversial.
Yeah, I don't know such examples. Yeah, what's kind of displeasing about assumptions like the algebraic group model is classic crypto assumptions are about what the adversary can't do. Like you cannot find X given G to the X, right? For example. And the algebraic group model, these non-falsifiable assumptions are assumptions about what the adversary can do. So they're kind of what the algebraic group model says is whatever the adversary outputs a group element, then the way you're assuming, you need to assume that the way he manufactured this group element is by a linear combination of group elements he's already seen.
Yeah. This is not different from the random oracle model, right? It's the same. And the random oracle model is so pervasive in practice.
Why is it not different? I mean, they're both wrong. But...
For instance, you assume that for the purpose of analyzing practical protocols like the one you use to shop in Amazon, you assume that if you computed, say, an image of an expanding function, then you must know the pre-image. So this kind of things, random oracle buys you, and it allows you to prove. And this, you know, when you want to prove anything related to blockchain, anything related to TLS, again, I'm not saying these assumptions are much more aggressive, if only because they can be completely broken because we don't understand the bilinear math good enough. But that's a different level. The point is that generic models exist even, you know, in the unstructured world of random oracles, and they're very problematic and have been heavily debated on the theory side, but in practice, people seem to be content with this, making this heuristic leap of faith. Here, of course, it's a very important line of work to try and get better assumptions, but I'm saying that from a clean math perspective, you can just model this as a random group and then ask your questions, and now they are totally unconditional, right? They do not depend on any crypto assumption.
I don't know if it's enough to, so what you need for the security proof of this thing is that when the adversary outputs a group element that is allegedly a commitment, that you have you are given the coefficients that with which he generated from the setup the commitment, and that allows you to extract. So I don't know if it's just about being a random group.
I mean, you assume that the adversary interacts like in the random oracle model, that you can see that the extractor or simulator, you can see which queries are made to the oracle, right? It's not just about. But again, I'm not. That's a speculation. I'm speculating that this can be proved unconditionally. That this has information theoretic or unconditional soundness if you pick the bilinear group at random. Okay, if you assume that you have oracle access to random bilinear group, I just can't see where, you know, the assumptions you're making, why they would not be provable in this generic model. Maybe I'm missing something.
So I suggest we take this discussion offline, because not all of us
Yeah.
are familiar with these models.
Yeah. Okay. Yeah, that's an interesting direction. Yeah, if something like that. All right. Yeah. So okay. So that. Okay, this has been, and especially if you didn't follow the last discussion, that's been sort of motivation for the model that I'm showing you now. which is sort of the model I'm plugging, you could say. So this is something I call polynomial protocols or idealized polynomial protocols. And so what does such a protocol look like? The protocol has some pre-processing or input stage where there's a prover and verifier. And in this first stage, we agree on some set of polynomials of degree less than d. Right? There's some d we all know, some degree bound, and this f smaller than d means univariate polynomials of degree smaller than d. Okay. And now, so the protocol definition.
What's the quantifiers here? Like, do you pick them? Can you pick them at random? What do you mean by agree on? Like, I don't understand.
I mean that the protocol is defined by these polynomials.
Okay, so, but for your purposes, picking them at random is good enough, or you might want to pick them in a different way?
Oh no! Usually they won't be random. They'll have some structure.
For example, the protocol specifies some distribution over polynomials, and you want.
It's not a distribution. It's not a distribution. It's for example, these G's will encode sometimes will encode the structure of a circuit you're proving things on.
Okay, so this is part of the specification of the protocol. Is these polynomials? Once you pick these polynomials, they're wired into the protocol. Okay, that's what you mean.
Yeah. Okay. And now, how does the protocol work? So the messages of the prover, we think of them as always going to some ideal party. And the messages must be polynomials of degree smaller than d. If the prover tries to send something else, then everything is aborted. So, the protocol proceeds, the verifier, sends messages that are usually random coins to the prover. The prover sends more polynomials. And then what happens at the end? At the end, the verifier chooses some constant number of polynomial identities. And we'll see an example pretty soon. And asks the ideal party, do these identities hold between the pre-processed polynomials and the polynomials the prover sent? And the verifier accepts if and only if the identities hold.
Can you express these identities as like linear functions or low degree polynomials in the coefficients of the polynomials that the prover sends? Like I'm just trying to understand how this relates to standard recent models of proof systems like IOPs or polynomial IOPs. Can you cast your model as an instance, as an extension? Is it more general, less general, incomparable?
It's less general than polynomial IOPs. Mm-hmm. Because I assume you're checking some identities between the polynomials, which will sort of correspond to sampling all the polynomials at a random point, whereas a polynomial IOP, you don't necessarily have to sample your polynomials at a random point. So it's a little less general than recent models. Okay, so is it clear what this protocol is? Okay, and now I want to define the complexity measure for this protocol. Like and the complexity of the protocol is simply the sum of degrees, or degrees plus one, the sum of degrees of the polynomials the prover sent. So that is the complexity of the protocol. Very simple.
T was L before?
FFT. Yes, thanks, Amir. Yeah.
I'm just trying to understand.
And Ariel, what
Yeah.
this metric that you defined, what complexity measure of the final protocol will this correspond to?
All right, so this exactly corresponds to this theorem. So why am I defining this measure? Because the cool thing is that using this polynomial commitment scheme, I can compile such a protocol to a real one, assuming these strong crypto assumptions like the algebraic group model, and the prover complexity will be very, 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 very close, up to constants to this sigma of p. And just to give you a feeling, so how does this compilation work? So in the real protocol, right, whenever the prover sends a polynomial to the ideal party, in the real protocol, he sends a commitment to the polynomial to the verifier. And then when, if in the ideal protocol, the verifier asks the ideal party, does this identity hold? In the real protocol, the verifier will choose some random z and ask the prover to open all these polynomials at this random z and check the identity on this random z. And then the question is, well, how much does the prover work in this compiled protocol? And almost all the work will be computing all these commitments, and computing all these commitments, it will exactly be this sigma p. That will be the number of elliptic curve operations.
Right, but you also have an FFT cost, do you also have an FFT cost, non-cryptographic cost, or like?
Yeah, that's a good. So there will this come up because we're going to have to talk about some quotient polynomial that often the prover will need to compute. So, so here I've taken some liberty to just push, not address the FFT costs, and this has to do with that in practice the prover, although asymptotically the FFT is n log n operations, which is the dominant part. Practically speaking, the elliptic curve operations are, at least till now, have been the dominant factor.
Up to a point, right? If you try to scale it to very large computer, if you try to scale it beyond a certain point, FFT will kill you. Also not only time-wise but also space-wise.
Yeah. Maybe, yeah. I mean, there's also work now on sort of avoiding FFTs, but yeah. Right now, this omits the FFT costs, and it may not capture all. We may need to add some factor related to FFT cost but right now, yeah.
But you're saying that for the instances, for instance, that are useful for what your company and others are doing, then the cost is dominated by the cryptographic cost and not by FFT. That's what you're saying, right?
Yeah, the elliptic curve operation. Yeah.
Mm-hmm.
Right. Okay. So, yeah, any more questions? Okay, so first, I need to, if you've worked on, like some people here on PCPs and proof systems, you may be thinking, okay, this model is nice, but it doesn't capture exactly what usually comes up in proof systems. Because usually we're not exactly checking polynomial identities, we're checking polynomial identities on a certain predefined range. And this relates to the following sort of variant of the definition, which is ranged polynomial protocols. So ranged polynomial protocols are the same thing, almost, but now the protocol definition also includes some subset H of the field. And now how does the protocol proceed? So same thing, the prover sends polynomials of a certain degree. But in the end, when the verifier decides to accept or reject, he doesn't ask if, he asks if the identities hold on this subset H instead of globally. And a nice thing is that we can move from one to the other pretty easily. And this will be a good exercise to see we understand the terminology. So suppose I want to simulate an H-range protocol using a polynomial protocol. So how does it work? Well, so suppose in the H-range protocol, I'm checking two identities. And so how do I simulate it? Well, I let the protocol run as usual. And now when it comes time to check the identities, V will choose two random coefficients and send them to the prover. The prover will send some additional polynomial T. And now V will check the identity A1P1 plus A2P2, is it equal to T times ZH, where ZH is the vanishing polynomial of the set H. So if both identities held on H, it means that both P1 and P2 were divisible by this ZH. So also a combination of them will be divisible by ZH. And therefore the prover can send us this quotient polynomial T that proves it.
So you're assuming that H is very small?
Why very small?
Because I thought you need everything to be low degree.
H is I don't know if I'm not sure what you mean by very small. H is like n. I don't know. It's like polynomially large, or
It was not part of the cost.
Okay, so what all right, so the cost here will I don't need to pay for ZH because that can be a pre-processed polynomial. What I do need to pay for here is T, is sending T.
Ariel, shouldn't the degree of T be something like the degree of the PI's minus H?
Exactly, yeah.
Okay,
So this thing, it motivates this definition that for an H-range protocol, we'll define its complexity to be, as before, the sum of degrees of the Fs, plus sort of what we're going to pay for this sending this quotient T, which will be D minus H, where D is the maximal degree of a identity that comes up in the protocol. Right. So any I guess that's a lot of definitions. Any more questions? I'm going to give, by the next thing is going to be an example of such a protocol, and it's going to be a little less abstract. But please let me know if there's any more questions. Okay, cool. All right, so now let's see a common example of such a protocol. So it's going to be for multi-set equality check. So forget polynomials for 1 second. Suppose I had two vectors, and I want to check that they're equal as multisets. So the simple point I want to illustrate is that I can reduce the multiset check to one product check with randomness, right? Because say I choose a random gamma, and now right, I mean, the products of the A's and B's can be the same even if they're different multisets. But if I choose a random gamma and I compare the product of the A's and B's shifted by gamma, then if they're different as multisets, it's sort of like I'm evaluating different polynomials at a random gamma. And I will get a different product. They'll be different with high probability. So in the polynomial world setting, suppose now I have two polynomials of degree smaller than d, and I want to check that their multisets of values on H are equal. I want to design a protocol for that. So this is because I can reduce a multiset check to a randomized product. This reduces to so say my H now, my set H is powers of some element alpha. Then checking that these multisets are the same can reduce to just comparing the products of the polynomial values when I just shift both these polynomials by this random gamma. So a tiny interlude. I'm going to assume from now on that my set H is a multiplicative subgroup of the field. So it's a set of powers of an element alpha, where alpha to the n is 1. And I'm going to make use of the Lagrange polynomials of the set H, which is just a set of n polynomials such that Li is 1 on the ith element and 0 on the others. All right, so now let's see such an H-range protocol for checking that the products of values of two polynomials are the same. So P, the prover will compute a polynomial Z which will sort of aggregate the values of f over g. So the z starts at 1, and then z at alpha to the I aggregates the product of f over g on the first I minus 1 points. So the prover sends this polynomial z to the ideal party.
So do you interpolate to get a polynomial, or?
Yeah, the prover will interpolate to get this z. So now V needs to check two things on this z. First of all, that it starts at 1. So, right, we're in this abstract model where we need to do checks on all of h. But if we want to check just something at a point, we can do that by multiplying by a Lagrange polynomial. So this first identity, L1 times z minus 1 equals 0. So that being 0 on all of h is exactly equivalent to z of alpha equals 1. So this first check exactly checks that z starts at 1. And now this second check, it's checking that really z is accumulating the values of f over g. So, right, it's checking if you divide by g that the current value of z times f over g is equal to the next value of z. So these two checks are showing us that z starts at 1. At every point, it's accumulating another value of f over g. And since the group wraps, it also shows us that after it accumulates the last value of f over g, that it ends at 1. Or in other words, the product of f's values on h is equal to the product of g's values on h. Any questions? So now the question is, what's the complexity of this protocol? So the prover only sent this polynomial z, which has degree n, and the identity. If you look at like the second row, the 3.2, we're checking an identity of degree 2n, because it's like z times f. so we have this factor, like the degree of the identity minus the size of h, which again will correspond to this quotient polynomial, which will be sen. So it's 2n minus h. H is also of size n, so we get 2n. Okay, so that was one example of this terminology. And now I want to sort of conclude the lecture by a second example, which, I mean, this multi-set check, I don't think you can improve it much. I think I'm guessing it's pretty tight. But the second example of range check, I'm hoping there's something much smarter you can do, and this is sort of what I wanted people to see and maybe potentially think about. So range checks. So here I have some integer m, and I have some polynomial f, and I want to check that all of f's values on h are contained in 1 to m. And okay, so like I sort of apologized in the beginning, there might be a lack of like context and motivation here, but basically this operation of a range proof turns out to be an extremely perhaps the bottleneck in the concrete efficiency of these snarks. And one reason for it, so here I'm saying a few sentences, something that maybe requires some context, but one reason this is the case is that something very important in snarks is recursive composition, where I want to make the program T that I want to prove things over is a snark verifier itself. And for reasons having to do with these elliptic curve groups that people use, this ultimately boils down to simulating. You have some field FP where you can do operations very efficiently, like your unit of cost is like 1 multiplication FP is 1, but you need to simulate operations in some other field FR. And typically how you do this is you decompose your elements of FR to these smaller limbs such that the product will not wrap around P, so you can sort of simulate their product without being worried about the reduction being the wrong modulus. But this decomposition to limbs, you need to like now verify that really now this field element, it's in some limited range. It's in this range 1 to 2 to the 64, say, or something like that. So yeah, so this is sort of the typical, like your field is of size 2 to the 255, and your range, your M here is going to be like something like 2 to the 64. So these range proofs end up being a lot of the concrete cost of in the ZK snarks. And this leads to this question. I have some committed polynomial, and I want to check that all its values are in some bounded range 1 to m. So now let me show you the sort of protocol we have. And like I said, we're looking for potentially better, smarter protocols. So first, let's make this simplifying assumption that the range, like all these values are contained in the values of f. And we're just checking that there's nothing outside of like this range. But yeah, so how does the protocol work? The prover will compute a sorted version of f. So just some other polynomial s that has the same values, counting multiplicities. Yeah?
I'm a bit confused a little bit. The fields you're talking about, there is no order on them. There is no, like the numbers 1 to m are ordered.
Right. Yeah.
The field in some, you have something in mind and I don't have it. Can you explain? Is it a general, an arbitrary set of size m? You want a concrete set of size n?
So the set, say, yeah, the field, yeah, it's some prime field of, say, where I'm thinking of the elements being from 0 to p minus 1. And then m, this big M is some integer much smaller than p minus 1.
So,
and I'm thinking of just the order.
So f is a prime field in this example.
Yeah, f is a prime field, and I'm just thinking of the sort of order from the integers. So I'm just thinking of each element as a representative from 0 to p minus 1. And yeah.
What is special about this set of points?
About what? The set 1 to m?
Yes.
You have bit decomposition, for instance, right? So you can, if I can prove to you that something is a small integer by giving you the bit representation, you can verify it. You cannot do it with an arbitrary set.
So it depends on if we agree beforehand on some other order on the numbers, then we can. I'm just trying to.
No, but you cannot. I cannot convince you that if you pick a random sparse subset of a field, that's a hard problem computationally. Whereas computationally, it's an easy problem to convince you that the binary representation of the field element in the way that Ariel described is from 1 to 2 to the 20, right? I just give you 20 bits and you verify by, right?
So let me stop you for a minute. So we're out of time. So I think we just go on because it's not done. But feel free to leave if you have to go somewhere else.
Oh, okay. So yeah, I'll try to wrap up pretty quickly. Yeah, I'm not sure this answers your question, Amir. But if for some other subset you could make a more efficient range proof than like range check, then that might be useful. But yeah, but since we're for this decomposing things into like small limbs, usually the range 1 to m or 0 to m is the convenient one. Yeah. Okay. So how the protocol works is P will compute this this sorted version of f, where so S is some polynomial getting the same values, but S of alpha to the I is going to be smaller than S of alpha to the I plus 1. And just P is going to send this sorted version of F to the ideal party. And now V is going to do a multi-set equality between S and F. So that's what we saw before. It's going to check that really S has the same values as F. And after that, right, it suffices to check that S's values are in the range. And it's going to be easier because S is sorted. So V is going to check that S really starts from 1 and ends at M. And right with these Lagranges, we can do these point checks. And now V is going to check that really each time we go forward to the next value, it changes by either 0 or 1. Okay, and since we're out of time, I'll sort of but right, the reason this was easy is sort of because we assumed that the values 1 to m are already in F's values. So generally, what we're going to do is we're going to have some pre-processed polynomial that is guaranteed to contain the values 1 to m. And then we're going to sort of do the same thing, but we're going to sort of use F union T instead of F. So we're going to have a sort of version of F union T. We're going to check that it's correct, and then we're going to check that really S only increases by 0 or 1.
So it seems like you only need to have 1 and m in the range. Why do you need all the rest?
Well, I need to check that really.
Because you have the multi-set equality, okay?
Yeah. I need to check that really. So I know that it starts in the range, it ends in the range, but now I need to check that it only increases by 0 or 1, that it doesn't like go way out and come back.
And for the multi-set equality, so you need the number of times that each element appears to match, no?
Yeah. The multi-set equality guarantees that.
Yeah, but you actually know that? You don't know how many ones, how many twos, and so on.
I don't know. I don't know.
Hello, Aryan, just one question.
Yeah.
Why do you go out of M? It's sorted, right?
Yeah.
So when you are increasing, isn't this an upper bound on the values that you're taking as you go along, as you go in H?
I need to check that I'm not going out and coming back. And the way I check that is this check 3.4 that checks that I'm only moving by 0 or 1.
So what I'm not getting is if S of alpha to the n equals M, then doesn't it bound all alpha to the I by M? So
why does it bound it?
Because S is sorted, right? S of alpha to the I is less than equal to.
Well, I need to check. The verifier needs to check that it's sorted, and in this
Okay.
3.4 implies that
yes.
the way.
Yes. Sorry. Yeah. Got it. Thanks.
So sort of the heavy thing is like I'm checking that it's sorted. To check that it's sorted with a really low degree equation, I need to move only by 0 or 1. But then the thing is, to be able to do that, I need to pad my values that really all of 1 to m will be there at least once. And when m is like 2 to the 64, that becomes infeasible. So I'd like, I guess, a way to check, for example, that S is sorted without having to do these tiny steps and having to pad with so many of these values. Yeah.
By padding, you mean the T, right?
Exactly. Yeah. Yeah.
And do you have a conjecture what
baseline is like order of n times log m. That's the bit decomposition approach.
The bit decomposition approach.
Like what would be the generic cost of doing it? Let's say using the bit decomposition, right? The limping. So can't you do it with like log m times n or something like this? What would be a generic solution to this? What would be the generic solution?
Well, right. So sort of you can sort of decompose your elements to smaller, to like bits.
Yeah.
And then now your range is in a sense just 0, 0, 1.
Yeah.
But you've paid, yeah, it's a trade-off. You've paid this multiplicative log capital M. Like I could, one thing to do is the prover supplies this auxiliary polynomial with all the bit decompositions of all the elements. And now on this auxiliary polynomial, I'll just do range checks in the tiny range 0, 1, which is easier. But now, yeah, I've paid this auxiliary polynomial of degree, yeah. And like you said, I guess I'm just n times log capital M. So, in sort of with this approach, you get, sorry, in the bottom, it should be capital M. You get, if you look at the sum of degrees, you get, like, you don't have, instead of n times log capital M, you get some n plus some 4m. So you don't have the multiplication, but you have capital M instead of log M. So the ideal thing would be if you could get like, say, 3n plus square root, for example, square root capital M, for example.
I'm not sure. Why can't you get using the same thing? I'm not sure that I understand. You get 10 times square root of n.
How would you do that?
Binary representation is one way to represent numbers. You can represent them in square root of m representation.
Right. So we're really playing here with constants. So what you could do, and what we do sometimes do, you could say, all right, I won't decompose to bits. I'll just decompose to, I'll decompose each element to 2 elements in the size square root m. Yeah, and then if we're just thinking asymptotically, you'll get like this 3n will become like 6n, and then this 4 cap m will be 4 square root m. So yeah, sorry, this is maybe where I did not, the open question, I didn't say it precisely enough. The question is, so that we know, this decomposition to the smaller range, we know, can you do something that is more effective than this decomposition to,
Okay, so any further questions? So let's thank Ariel for this very interesting talk and this intriguing open question. So I'll stop the recording now, and you can continue talking if you want.
thank you very much. Yeah, I think I need to write more, and I'm really glad it came up from Amir and Yuval. I should write more generally what you can get from decomposition to bits or blobs. I should write explicitly what you can get from decomposition, and sort of say the question is to do better than that.